Today I'll be sharing my talk on hardware-accelerated spiking neural networks based on zero-field skyrmions. This was done at the Institute for Materials Research and Engineering at A*STAR. So, neuromorphic computing can be best described as brain-inspired computing, which consists of a vast interconnected network of neurons and synapses. Man-made devices typically adopt a crossbar array architecture of synapses and neurons to represent this vast network. So why are we interested in this topic of neuromorphic computing? It is because the computational power of the human brain is comparable to an array of high-performance computers while using only a fraction of the energy and space. So successful development of such devices would thus be highly relevant to applications in computationally intensive tasks like pattern recognition and machine learning. So our brain is made up of a dense array of neurons connected by synapses, and essentially the membrane potential is determined by salt concentrations and whether ion channels are opened or closed. A signal is transmitted from one neuron to another when the membrane potential at the synapse exceeds a given threshold potential. And this naturally occurring behavior is much more complex than what I've described. It was first proposed that neural networks be reduced to a simple mathematical construct, which is aptly termed the artificial neural network. More recently, spiking neural networks have been proposed, and these networks resemble the mechanics of the brain more closely. So I'll be elaborating more on the second type of neural networks. So in a spiking neural network, information is contained in a time interval between spikes, while the spikes themselves are binary in format. So they are just binary 1 or 0. So information can be transformed into this format by techniques like rate coding. For example, the higher the intensity of the pixel in a binarized image, the higher the frequency of the spike at that to represent that pixel. So an ideal spiking neural network contains neurons that follow a leaky integrate fire model. So to illustrate how this works, consider a simple neural network with 3 presynaptic neurons connected to one postsynaptic neuron. On the right is the time evolution of the membrane potential and spiking input of the postsynaptic neuron. Initially, the membrane potential of the postsynaptic neuron is at the rest potential. When one of the presynaptic neuron fires, the postsynaptic neuron will register a spike, causing the postsynaptic membrane potential to increase. So this process will repeat if another presynaptic neuron fires. And given that the threshold potential of the postsynaptic neuron is represented by the red line, the postsynaptic neuron will fire once it reaches this potential. The postsynaptic membrane potential would then return to its rest potential. So this is the basic mechanism of the leaky integrate fire model. And notice that if there is no input spikes for some time, the membrane potential will decrease, which is a biologically realistic feature. So other requirements for an ideal neuromorphic device is that they must be able to perform multiplication of the signal and the synaptic weight, and be able to sum up the signal of the postsynaptic neuron, and be able to read out the spike once a neuron fires. So our proposed device makes use of skyrmions as the information carrier due to its room temperature stability, energy efficient manipulation, and particle-like localization. Additionally, the spatial temporal motion of transmitters are reminiscent of the motion of skyrmions along the racetrack. So skyrmions are a good choice for signal transmitters for spiking neural networks. So the device that we are working on hinges on interlayer coupling interactions, specifically the effect of RKKY interaction and dipolar coupling. RKKY is the electron-mediated long-distance exchange coupling between localized magnetic moments in metals. The energy associated with RKKY interactions are dependent on the distance between spins, and in a while I'll be showing how this forms the basis of our work. Another effect that we have to account for is the dipolar coupling, which we have also exploited to realize skyrmion cloning. So the material stack that we use consists of 3 types of layers. The chiral layer is a soft magnetic material with low anisotropy. The IEC layer is made of a spacer material, while the bias layer is made of a hard magnetic material with high anisotropy. Previous work from our group also showed that by tuning the IEC layer thickness, zero-field skyrmions have been experimentally observed in the chiral layers. So RKKY interaction is the next neighbor interaction, and sub-nanometer changes to the thickness of the IEC layer can have significant effects on the magnetic behavior of the sample. It's thus possible to spatially vary the RKKY interaction by making small changes to the thickness of the IEC layer at a particular region, as illustrated here. This allows us to control the effective magnetic field applied at different regions on our device, and is critical for realizing skyrmion manipulation at zero applied field. Because we want to use skyrmions as a signal for our neuromorphic device, we must first understand that the motion of skyrmions under an applied current is not ideal from a device perspective. In particular, the vertical component of the skyrmions would cause them to annihilate at the edge of a wire and cause us to lose our signal during signal transport. This phenomenon is known as the skyrmion Hall effect and arises from the gyro vector term in the TLE equation. So the first thing we have to do is to engineer the IEC layer such that we can suppress this unwanted effect. This is summarized by the graph over here, where we can see the vastly reduced percentage of skyrmions annihilated at the edge of the track when the IEC layer is spatially varied. It should also be noted that with IC engineering, annihilation only occurs as skyrmions enter the interface and no annihilation occurs thereafter. And an added benefit is that with IEC engineering, we are able to increase skyrmion velocity and reduce skyrmion size, allowing for faster and more compact information transfer. So this has to do with the energetics term, where the effective field increases the Zeeman-like energy, which repels the skyrmion away from this interface, causing it to move in a straight line. So the next thing we want to do is to introduce our LIF neuron. Here we have mu-max simulations showing how the magnetic textures evolve over time when we pulse a current through the track. Skyrmions are artificially inserted at a periodic rate into these simulations, and we first define a few terms as shown here. The membrane potential of a neuron refers to the number of skyrmions at a readout. A signal of 1 refers to a skyrmion input, and a signal of -1 refers to the firing of the neuron. The neuron fires once the membrane potential reaches a given threshold, and in this case, the threshold has been set at 15 skyrmions at the readout. Firing is simulated by passing a current in the opposite direction. And if we now look at the graph over here, we can see that after a certain delay, input spikes result in neuron integration as the membrane potential increases, while firing resets the membrane potential. The leaky behavior can be observed when the neuron receives insufficient input stimuli. Here we see that when there is no input spikes for some time, the membrane potential decreases. So for the synapse, our synaptic device consists of 2 perpendicularly stacked magnetic racetracks separated by a non-magnetic electrically insulating spacer layer. Only dipolar coupling is present between the 2 layers, the 2 tracks, and there's no RKKY coupling between the 2 stacks, and no current would flow from one racetrack to the other. If we now define the weight as the number of skyrmions in the intersection region of the skyrmion generator racetrack over here, we can set the weight by applying the corresponding number of pulses through the bottom racetrack, as this will nucleate the desired number of skyrmions in the intersection region. This architecture also allows for skyrmion cloning because the stray fields from the skyrmion in the skyrmion generator racetrack will induce skyrmion nucleation in the top racetrack, and a pulse through the top racetrack is sufficient to overcome the dipolar coupling and share the skyrmion copies along the top racetrack. So here is a short simulation result of what we have obtained. And now if we define the number of skyrmions in the top racetrack as the output signal, we can see that the output signal is the product of the number of chiral A pulses and the number of the pulses through the top racetrack. So in summary, these are the main requirements to build a neuromorphic device, and this is our current progress. There are many different ways to fulfill the requirements of a neuromorphic device, and there have been many proposals that do not involve skyrmions or spin textures. But comparing our device to those that do use spin textures, the novelty of our work is that we work with zero-field skyrmions. We have a relatively simple design, and we can dynamically tune the weights in our synapse. Additionally, our device is crossbar array compatible, ensuring device scalability. So I'll end this with a schematic of how our proposed device will look like. Yeah, thank you.
Thank you very much, Nicholas, for the excellent talk. That was very interesting. Do we have any questions, either in the chat or you can unmute yourself and ask that way?
Hello.
Hello, we can hear you.
Yes, could you please explain the three-use equation? Hello.
Sorry, I couldn't really hear that.
Am I? Sir, can you explain the three-use equation, which contains the Magnus force?
The Thiele equation.
High-use equation you have written in your PPT.
Yeah, so oh yeah, this equation.
Yes, this one.
Yeah, so it's quite a complex equation, and it will take quite a bit of looking through, because it's a matrix thing, and so there's actually a x component and a y component, and when you have the gyro vector term, it basically contributes to the y component of the skyrmion velocity. So that is, I think that is the easiest way I can explain it, because if you would like to know more, this is quite an in-depth equation that requires quite a lot of looking into. Yeah.
Okay, thank you very much.